Having this year. Someone up. Plugged in. You switched up and not the problem.
You want to go? Just the painters. I know. The Friday or Saturday before. No. Just for the bottom.
I don't know what's going on here.
Is that projector not working?
It seems to not be working. I have no idea why.
No, because I was asleep before she got back.
That's the right button.
Shouldn't have just go to like my green from the projector?
That's a good question. I don't actually know. I turned it off before that.
What HDMI is that one?
It's plugged into the right one. Because we want the computer plugged in, and that's this cord right here, which is certainly the one you plugged into the right spot. This one you do over here.
The computer talking first thing?
Good question. That's an excellent thing to check. Let's see here. Here's to be. Right. Let's see here.
The authorization on the computer?
So one more time?
Maybe there's just a cord on the computer's end is problematic.
That's how I just
You can try it with a different one.
but let's see if we change the dot cam. Not plugged in. Doesn't seem to be. I feel like it's a projector issue. Let me check. Let me see if there's been any conversation on our group chat about it. Nope. Okay. Well, talk amongst yourselves. Give me a minute. Yeah, sure.
Never mind, I have no idea. Let me check. Sure. I'm not announcing afterwards.
Those of you on Zoom are having some technical difficulties here, so we'll try and get started as soon as we can. And you can form.
I hope you have 2 hours, there's only been 1.
Oh. Let's try to stay in yeah. While I'm up here. 2 things. One, there is an evaluation fill out that's on campus, like the top of the modules in Canvas. So if you, when you have, it's not required, but I would appreciate you all filling it out when you have a chance. It's totally anonymous. I will read the feedback eventually when it gets sent to me, and I will use that to hopefully do a better job every quarter. So, yeah, please do fill that out. And then the second thing is that if you want to fill out the Google form to sign up to be added to the canvas for Co-21B, not code, for the 21B workshop next quarter, that is now available on the AATC website.
That's not on the canvas, that's on the website.
That's on the website, yeah. I can link to it from canvas, but I haven't yet. What is going on? Oh,
You didn't even show the Panasonic.
what's that?
You didn't show the Panasonic this time.
Yeah. So you all too, so just, in fact, I can share with you all, if you go here. You can certainly sign up for if you scroll down, you can sign up for oh my gosh, for 21B next quarter. What is, I am. Technical difficulties, causing difficulties over here. What is going on? What's that? I'm the problem with chocolate people on Zoom can't really see it. Otherwise, I would totally go there.
Yeah.
We'll give it a minute. Yeah. So you also check that out. Here's the attendance form again. Have it. The place where you can sign up for 21B code for the 21B workshop. Yeah, this is always great. Last thing. Here's what it is. We'll see. We get things situated while I wait here for. Not completely exactly. Okay. Oh, cross your fingers, hold your breath. Okay. Right. Yeah, okay. Doesn't bode well. Not saying something stupid, right? Like.
Is there something else you have to like, is it that green thingy that does it?
This thing here?
Yeah.
Well, actually, this can be problematic sometimes. If you've got this plugged into the HDMI, it'll prevent the computer from sending it signal. So I'm sure like this is not plugged into the HDMI. The computer is plugged in to its usual spot, right? Over there. I can try this. See what happens. All right. Well, I guess I'll let people know. Sorry. So I guess we'll try and chalk it up and I will try to make it as visible and I will try to say all the words to those of you on Zoom. Let me think for 1 second here. Yeah, let me communicate with my coworkers that we're having issues up here. Sorry for the delay. All right. Let's see, so let's try to make this as visible as I can for everyone. So. Yeah, you guys on Zoom are not gonna be able to see very well. Unfortunately, that is the life of the board here. Yeah, it's. And yeah, I can't know this. I'm trying to think if there's any other solution. We have no, not really. Okay, so I'll say a word. You all should ask questions if you've got questions. Yeah, sorry for the issues. So there were a couple problems that I saw in drop-in that were interesting before we do some review here. Yeah, there were these two questions that I thought were. One of them was the following. So get started here. We've got the following. So all the words. So we've got the function y equal to x squared plus a over 3x plus c. And we're given that this function has a local minimum at x equal to 6, and it has a local maximum at the point -1, -3. And our job, or the question being asked, is to find a, b, and c. Which seems kind of tricky. So, first things first, we have the point -1, -3 on our function. So I'm going to plug in -1 for x and -3 for y to get one equation. I'm just trying to get all the equations I can so I can start solving for a, b, and c. So I'm going to say, great, -3 has to equal -1 squared plus a divided by -b plus c. That's one equation. I'm going to end up needing probably 3 equations. So we got 3 unknowns. I usually need 3 equations to be able to fully solve that system. So that's one thing I've got, and I would probably multiply both sides by the denominator. Say -3 times -b plus c is equal to 1 plus a, or 3b minus 3c equals 1 plus a. Maybe I'll mess with that further to get somewhere else. All right, and then I also have a local minimum at x equal to 6. So that doesn't mean I can plug in 6 to this and know anything, but I know that if I take the derivative and plug in 6, it should equal 0. Technically, it can be 0 or undefined, but it's not undefined because the only place this function is going to be undefined is where it has a vertical asymptote. So it's not going to be where I have a critical point. I'm going to take my derivative. All right, so it's going to be the bottom bx plus a times the derivative at the top. Sorry, bx plus c, apologies. Times the derivative at the top, which is 2x minus the top, x squared plus a times the derivative at the bottom, which is b, all divided by the bottom squared. And actually, the question.
Really quick question. So I think I got what you said about non-existent. So non-existent could be a local min.
Well, right, but so here's the thing though. So this derivative, the only place this derivative is undefined is at the same place where this original function is undefined. The only place this is going to be undefined is where bx plus c is equal to 0, which is exactly where this is undefined.
So it's not critical.
So it's not a real critical point. It's still a place you might look if you're doing like a sign chart for the first derivative, but we're not doing that here. We're just using this information.
So the
So
local min.
right, exactly. So right, bx plus c equal to 0 is not going to give us a local minimum, so it's not going to be a critical point. Cool. All right. Jen's going to come up and see if she can help with things. So we've got 2 pieces of information. We know that when we plug in 6, this derivative should be 0. So y prime at 6 is going to equal now. Sure. Let's just plug in 6. So we get 6b plus c times 12 minus 36 plus a times b divided by some stuff that's not going to matter when I set this equal to 0. So I could divide this by 6b plus c quantity squared, but then when I set the whole thing equal to 0, it's not gonna matter that this denominator was there or not.
Well,
Well, when I set a fraction equal to 0, do I want the top to be 0 or the bottom to be 0? The top and not the bottom. Setting this equal to 0 just becomes setting the top equal to 0. So, yeah, that's terrible. So anyway, multiplying this out, you've got 72b plus 12c minus 36b minus ab equal to 0. Or simplifying a little bit, 36b plus 12c minus ab. Okay, then we do the same thing, we plug in -1, because -1 should also be a critical point because we have a local maximum there. So plug in -1, same sort of deal. And I can probably put a number here. Y prime of -1, hey Jen, should equal, let's see, plug in -1, same idea, we're gonna get, let's see, b times -1 plus c times -2, so we're gonna get -b plus c times -2 minus, we put in -1 here, we're gonna get 1 plus a. Again, I'm ignoring the denominator because we know. Simplify this a little bit, we've got 2b minus 2c minus b minus ab equal to 0, and then simplify a little more, b minus 2c minus b equal to 0. All right. So now what? Well, here's what I would say. We have enough equations. What do I mean by this? Well, how many of you have to take linear algebra at some point? 22A? Probably no, you don't? Okay, so
I think it's a prerequisite for 21A, way before 22A, no?
I was just asking how many of you have to take 22A?
We'll have to.
Yeah, at some point you have to not have taken 22A, have to take 22A in your future. Probably most of you. Anyone's really in the engineering track, 22A is correct. So something you'll see eventually is that when you have a system of equations, you need as many equations as unknowns to be able to solve it. And we have that now. We have 3 unknowns, A, B, and C, and we have 3 different equations. That should allow us either to solve it or show that it's unsolvable, because that's also an option. So what do we do now? We have to kind of figure out here's what I saw, and there's a lot of different ways to go there. I saw that both of these two equations have a minus a times. So what I thought about doing was saying, well, on that equation there, b minus 2c equals a times b. And this equation here, 36b plus 12c equals a times b. And if those are both equal to a times b, then these two things have to equal each other. So I can say that b minus 2c equals 36b plus 12c. But then I've got, let's see, 35b equal to negative 14c. I divided both things by 7 because that seems sensible. Negative 2c equals 5b. And then I thought about, I'm going to have to plug back into this equation over here. Okay, so here's what I've got. And I might go further. I might say c equals negative 5 halves c. But it's kind of just an algebraic, not fun method. Sorry for the Zoom folks over there. Hopefully you can hear something. So I've got the following. I've got my equation there. 3b minus 3c equals 1 plus a. And the idea now is I'm going to try and get everything in terms of b. We've got c in terms of b. I think this is 3b minus 3 times negative 5 halves b. And a. So I need to go back to one of these two equations and solve for a. Let's
then
pick.
you're gonna have
You're right, but I'm gonna plug that in there. So I might even do that first. I might take this easier looking equation and actually plug in what negative 2c is equal to first. So I'm gonna take that and say, okay, b minus 2c, well, minus 2c is equal to 5, so it's really plus 5b is equal to a times b. Oh, that's interesting. I hadn't even thought about doing that. I didn't do this last time. And so it looks like A might have to equal 6. You guys see that? B plus IB is 6B equals A times B.
Oh, yeah,
I think A has to equal 6.
yeah.
That's cool. Then we can solve for B. Interesting. Didn't think about that. So anyway, if I have this, I really don't want to get fractions. I'm going to multiply everything by 2. So I'm going to say 6B minus 3 times minus 5 is plus 15B equals 1 plus 6 is 7 times 2 is 14. So 21B equals 14. So B equals 14 over 21, which reduces to 2/3. And then finally, C is going to equal negative 5/2 times B, which is negative 5/2 and 2/3, which is going to be negative 5/3.
Oh, no.
Negative 5/3. So, yeah, it's definitely it's a tricky algebra question. Like there's a lot of different arithmetic and algebra here. But the thing that we started with was taking what they gave us, right? We had this function, and they told us a few things. They told us we had a local minimum at 6, meaning the derivative when we plugged in 6 had to equal 0. They told us we had a local minimum at -1, -3, which actually gave us 2 things. It gave us one, that when we plugged in -1 to the derivative, it also had to equal 0. Also, we plugged in -1 to the original function that had to equal -3. And those 3 different things gave us our 3 equations that allowed us to solve this. Question?
So when you had white prime of -1,
Uh-huh.
could have just divided, there's something that I noticed when I was at final with it, you could have done a B right there. Because if you divide both sides by negative B over B plus C, then you get -2
So
minus negative 3B, which is just negative.
So what I want to point out though is dividing both sides by anything here is iffy. It might be dividing by 0.
But don't you know negative B plus C can't be 0 because it would be undefined the function. Is that true?
Maybe not. I don't know. Let's see. Negative. I guess when you're plugging in, yeah, I suppose that's a fair assumption to make.
Yeah.
So you're saying we can take this equation and do what?
So if you divide the left side and the right side by negative B plus C, you
Okay.
get -2
Mhm.
minus negative 3B. Because
Wait,
we
wait,
have
wait.
3 out there.
Wait, we're taking this equation?
Yeah. You got both sides by negative B plus C.
Okay, so negative b plus c times -2 minus 1 plus a times b. If I divide everything by negative b plus c,
There we have -2.
sure.
And then minus 1 plus a over negative b plus c equals -3. We have that from the other equation.
Okay, sure. That seems reasonable. 1 plus a over negative b plus c. Okay, interesting. So while I agree with this, I don't feel like it's super easy to see. But yeah, that would also get you to b equal to positive 2/3.
Is that valid though?
I think so. I don't see why it's not valid. Again, it's not what I would see easily though. So while this works, it might not always be easy. Good question. So I was about to do something else. Because when I worked this problem out on my own beforehand. And at this point here, when I was trying to replace everything with stuff in terms of B, so like I replaced C with that. When I did this before, I replaced A with I actually took this equation here and I actually solved for A. What I really did in the past, I said B minus 2C equals A times B, and then I divided both sides by B. So that A was equal to 1 minus 2C over B. And then I plugged that in, and then I plugged in for 2C as well. So what I did was I said, oh, then I'm plugging for 2C, and when I plugged in for 2C, I got 5B. What I should have done, right? So I was going to plug that, and I was going to say, oh, this is really 1 plus 1 minus 2C over B, and then I took the additional step of plugging in two C equal to negative five B. Hold on, what's that? So what I did here was I said that was then negative five B. But what I should have done was what I did over here, where I said, oh, AB equals B minus two C, and then I replaced the, sorry, brain. AB, oh, sorry, sorry. This problem is a little terrible. So I did this, right? I said AB was equal to, I see, I skipped the step. AB was equal to B minus 2C. That's from here. And then I replaced the minus 2C with the positive 5B. So I got B plus 5B equal to AB. And then B plus 5B is 6B equal to AB. And then I divided both sides by B, which again, I'll admit might be dicey because maybe B was 0. Not, but it's, so maybe I shouldn't have actually done that. Maybe I should have just put it over there and solved it that way, but it worked.
Oh, I was just wondering for that part right below, or B minus two C equals AB, and it's Y minus two C divided by B equals A, because I understand that you divide by B.
Right.
But in the beginning was B minus two C, why is it now one minus?
One divided everything by B divided by B is 1.
Okay, oh,
2C
right.
divided by B
Okay.
is.
Yeah.
Yeah.
So when you make the assumption that B divided by B is 1, I should also make the assumption that B is not 0. You could divide after that,
You're
right?
correct. I am making this up that B is not 0. Okay. Yeah. And in fact, if you do, there's one path in this problem that leads to you getting B equals 0. But then B equals 0, you also get C equal to 0, and that doesn't work out because B and C are both 0, then this denominator is always 0, which is not.
So why is that not valid? Because I kept getting the same answer, B equals 0, C equals 0.
Sure, well, it's not
Any mistake in
because
that.
then what's your function?
I mean, I know that it wouldn't work with this function, but how?
Right, but this is the function we're dealing.
Okay.
So it's not, we can't really take that logic and apply it to some other thing that we don't know. But the idea here is that this has to be, right, you have to have a function where, right, you can't just have, your function just can't be x squared plus a divided by 0. That's not really a function that's defined anywhere. So that's why it doesn't work there.
But it's a sort of solution, it just doesn't work for this function.
Right.
Okay.
Cool. There's another interesting question I saw that we should look at. There's a similar but different flavor. It's all right. We were both failures. It's all right. So, sorry for the Zoom folks, but hopefully at least the words I'm saying make sense. If you have questions, don't hesitate to interject and ask me to clarify something. So the following question, I don't remember exactly. Oh, it's on my notes here. Yeah. So find A and B so that the limit as x approaches 0 of tangent of 4x over x cubed plus a over x squared plus sine of dx over x is equal to 7. Tricky problem. It's a good problem. It's not out of bounds tricky. So what I would point out first of all is we know what this one means. The limit as x goes to 0 of just sine of something times x over x. We can either do it the way I like to do it, which is say it's going to be the limit as x goes to 0 of sine of dx over x, and then fill in the blanks. We want what down here? It's up there. Cancel. That limit is you get 1 times 2. Or you could do it probably with the more intended way, which is to use L'Hopital's rule. Say that this is equal to a limit as x goes to 0. Your sine of dx is cosine of your stuff times the derivative of your stuff divided by the derivative of x is 1. You plug in 0 for x. And get cosine of 0 times b, and cosine of 0 is 1. You get b. So either way, the limit of that part is b. But then the other parts are, well, if you plug in 0 here, you get 0 over 0. Plug in 0 here, you get not 0, probably over 0. Yeah. So what I think is the right thing to do is to combine these two parts together in one fraction. Because it is true that if you take the limit of a sum, it's equal to the sum of the limits as long as each of the limits exist. So it is definitely okay to say, or at least to start off by assuming that this limit is equal to the limit as x approaches 0 of tangent of 4x over x cubed plus a over x squared plus the limit as x approaches 0 sine of dx. And that's equal to 7. And the other is equal to 2. Cool. So now, since this is 0 over 0, this is not 0 over 0. I know I'm supposed to get this to be equal to 7. I probably need to combine these together. I'm going to rewrite this as the limit as x goes to 0 tangent of 4x. And multiply this by x over x to get an ax for x cubed. And that should equal 7 minus b. Now, what kind of limit is that? Tangent of 4x plus ax over x cubed. And that's not a great question. What kind of indeterminate form is that one? Definitely 0 over 0, which means we can totally use L'Hopital's rule. Using L'Hopital's rule, this limit's going to be, let's say, derivative tangents and stuff is I integrate the limit. That's going to be 0. You're going to get, let's see, derivative tangent of 4x is secant squared of 4x times 4 plus the derivative of ax is a over 3x squared. And now if we plug in 0, what do we get on the bottom? What do we get on the top? Let's see, secant of 0 is 1 times 4 is 4. So you get 4 plus a over 0. Yes, unless a is equal to what? Right. A is equal to -4, then this is still a 0 over 0 type of limit, and we can use L'Hopital's rule again. So we say, oh, it's probably going to be the case that a has to equal -4. So then we can use L'Hopital's rule again.
That's just an assumption, right?
Right, but the thing is, we're making that assumption based on the original given fact that this limit is equal to 7. Right, if a wasn't -4, then this limit would be a non-zero number over 0, which is some sort of infinity. It's not going to work for us because the limit needs to be definitely not infinity. So it's a pretty safe assumption to say, it needs to be true. And then using L'Hopital's rule, okay, derivative secant squared of some stuff is secant to the power of 2. So you got something squared, the derivative is going to be 2 times that something times the derivative of that something. The derivative secant of 4x is secant of 4x times tangent of 4x times the derivative of the inside stuff, which is 4, times the other 4 that was already there.
Wait, that means why for the chain rule can you just do like bring down the 2 and then instead of like in my head how I thought you would do it is like it'd be 2 times already secant times tan and then times the derivative of 4x, right? But then you just
Right. So I got the derivative of some stuff squared. So the derivative of something squared is 2 times your something to the first power times the derivative of that something. But then the derivative secant of some new stuff, well, the derivative secant of x is secant x tangent x. So the derivative secant of 4x is going to be, well, the derivative secant of 4x is going to be secant of my stuff, tangent of my stuff, times the derivative of that stuff.
okay, that makes sense. if it was just secant 4x and it wasn't squared, then you would do, it would just be like secant and tan of that stuff and then the derivative of that stuff.
Exactly.
What are we solving for in this problem?
We're talking for A and B.
Oh, yeah.
So we already got A, we're still going to get B.
Sorry, but
You
the
got-
second 4 comes from the 4 that's being multiplied.
Right.
So it gets split.
Right, this 4 came from when we took the derivative change of 4x. We got secant squared of 4x times 4.
Okay, cool.
So now all of this is the derivative of secant squared of 4x. And there's still that 4 over there.
Okay, cool.
Plus 0. All over 6x. Here's where life is terrible. You plug in 0, what do you get? What do we hope we get? We want this limit to exist.
Zero.
Right, it better be 0 over 0, otherwise we're gonna have problems. Wow, 0 over 0, I really don't want to use L'Hopital's rule again. Right, do you want to take the derivative of secant squared times tangent? No, you do not. I don't either. Luckily, we don't have to. This is a place where the tools you have aren't always the tools you want. Meaning, L'Hopital's rule totally applies here. You totally use L'Hopital's rule and you're totally terrible. Better, smarter, wiser thing to do is to recognize that you have a sine of x over x. I'm going to rewrite this as the limit x goes to 0. Let's see. Tangent of 4x is really sine of 4x over cosine of 4x. What I really have is a sine of 4x over x times all the rest. To secant of 4x. I guess I could have been smarter about that. Could I have my never mind. I couldn't be smart about it. Secant of 4x times another. I guess I could write secant squared of 4x. I can slightly square. Let's see. 2 secant squared of 4x. I guess I can multiply times the 4 times the 4, and then my tangent of 4x. I already captured the sine there. I still need the cosine down here. And then this. That's the same. Let's double check. Sine over cosine is tangent. Cool. Secant squared. 2 times 4 times 4 over 6. Yeah, it's the same. Okay, everybody. Here's why. Show me on your fingers. What's the limit of sine of 4x over x?
1 over 4, no?
No, it's not 1 over 4. Show me on it. You have the right number of fingers to show me on your fingers. It is this thing. Right, it's not sine of x over x, it's sine of 4x over x. So if you wanted to, you could toss in an extra 4 here and an extra 4 here. And then that limit's defined. And everything else is defined when you plug in 0. You're gonna get 4 times 1 if you like, times 2 times secant of 0 is 1 times 16 over 6 times cosine of 0 is 1. This ends up equaling something terrible. 32 over 3. Okay, but this limit was supposed to equal, this was supposed to equal 7 minus b. So then b is equal to 7 minus 32 thirds.
Then it's 64.
Did I miss a 2 there? Yeah, I guess I did. Fine. 64 thirds. Crazy, right? It's a crazy problem. But it is definitely do now. I couldn't imagine someone asking like that's not, or in my I mean,
I hope not.
it's not totally reasonable. It's moderate. Yeah.
You said that someone assigned you this for homework.
Yeah, this is a homework question. One of like many homework. Right, this is like problem. What problem? Where'd you go? Problem something on this other page. So like problem 13 of, I don't know, of 20 some. Good times. Question.
So you have help because you know that tangent of 4 is over.
Before you both go, let me just give you. I've got some samples. work on it.
Thank you so much.
Oh, yeah.
So tangent of 4x over x without x cubed. Limit of x approaches 0 for that is just 16, right?
Nope.
Isn't it?
Nope.
Sine 4x over cosine 4x. And you just times 16 over 6, and then 64. 64 over 64.
For this limit here,
Yeah,
the limit doesn't exist.
sure.
Yep. So if you do the limit as x goes to 0, if it was tangent of 4x over x, it would totally work. If we're tangent of 4x over x cubed, it is a 0 over 0.
Why would tangent 4x over x work? That just be 1?
It would be 4.
4.
But
Oh,
okay.
So we can use L'Hopital's rule.
I'm thinking of a different way of doing it though.
What way is that?
So you just decompose that to sine 4x. Oh yeah, you're right, you're right. It had to be sine tangent of cube 4x.
Right,
then
because the stuff has to be the same stuff and it's not the same.
that's true for
Yeah.
cosine too.
No, it's not true for cosine. The reason it works for tangent is because tangent is sine over cosine. So whenever someone says something like the limit as x goes to 0 of sine of x over x equals 1, that's totally cool. And it's also true for tangent. Limit as x goes to 0 of tangent x over x is 1, because really tangent x over x is just sine x over x times 1 over cosine.
So then what happens to the cosine?
Good question. So what happens to sine x over x?
1.
Right, and then if you plug in 0 for x, what's cosine of 0? So that's why it works for that. So basically, limits that go to 0 for like sine work kind of the same way as limits that go to 0 for tangent. Tangent and sine are kind of interchangeable when your stuff's approaching 0. Kind of. Cool. So interesting problem. Yeah, all right. So I have where this. So here's what is maybe not quite appropriately labeled as a sample final, but I thought we could go over some of the problems with this. And we'd have people just work on it, except Zoom folks. It seems weird to have people work on stuff in a class and on Zoom, like feels wrong. So I was just gonna start beginning, very good place to start. Yeah,
So either before this one or after this one, do you think you could just really quickly go over the definitions for critical point, inflection points?
sure,
There's a lot of stuff like this.
okay,
So, like, if I understand correctly, if the function isn't defined on one side, then can it be a local max or local min?
that is typically correct, yeah.
So it can be a local max or local min, even if it's on the endpoint.
No, your first statement was correct, sorry. It usually is not defined for max or local min.
Okay.
Because it really kind of depends.
Okay.
So,
Our homework assignment, they were.
yeah, so like, for example, for f of x equal to the square root of x. Which looks like this. Is 0, 0 a local minimum?
Is it closed? It's open at 0, right?
It's close to 0,
It is,
Yeah.
then it is.
yeah,
Because it's continuous over the closed interval.
well, is it continuous there?
Yeah, because it's defined for 0.
Well, so technically what I'd say is it's actually right continuous there. Which so typically you define this function, we typically say this function, f of x equals the square root of x. Is continuous on its domain. With the understanding that this at 0 specifically, it is technically right continuous. Meaning it is only continuous from the right and is not continuous from the left. Technically, according to our actual definition of continuity, we would usually say this function is not continuous at 0. To be continuous at a point, what has to be true?
Limit from the right side.
Right, limit from right and left have to equal. Oh, limit from left doesn't even exist here.
It's not that it doesn't exist.
It is certainly that it doesn't exist.
It's a different type of non-existent. though, right?
That's fair. So, but you're right. But typically in textbooks, we then say, okay, if we have a function, if f of x is only defined on one side of a particular point, 0 in this example, then we take continuity to mean left or right as makes sense. So yes, this function is continuous at 0, but maybe slightly differently. So now the question is, and I'm really asking you, I'm not saying I know, is this a local minimum? It depends on your teacher, to be honest.
Yeah. because
yeah.
my teacher said it.
Sure, that's totally fine. It's definitely a global minimum, for sure.
But does it mean that are all global minimum also local minimum?
That's what the homework assignment is saying.
Good question.
It was weird.
Is every global minimum a local minimum? I don't know. Maybe.
Does it depend on your teacher again?
I don't know. I really like, I mean, it seems like it should be, right? Because if you're global minimum, you're less than everything, you should be less than everything that's next to you. So let me look at the, let me draw a picture. So let's say our function look like this. I'm just gonna something kind of simple. All right. So, let's take this one. 2, 1 definitely is absolute minimum or global minimum, right? Why? What's that?
Is it?
Yeah,
Sure.
yeah.
But isn't extremum defined for continuous functions?
Absolute extrema. So the way, at least the way I find, so y equal to 1 is an absolute minimum. If f of 1 is less than or equal to f of x for all x.
Okay.
And I mean, I'm fairly confident, you make me question. I'm pretty sure we don't care about continuity when we talk about absolute minimums or maximums.
Okay.
But I could be wrong.
Yeah, our teacher said like it just has to be like a solid dot, like even.
Right.
If
So
it,
this something definitely not continuous, right?
yeah,
I think it's a little bit hard to distinguish when the teacher is talking about global or local.
Right.
Max.
So now let me ask you. Is this a local minimum?
No,
can it only?
Why not?
Is there an
Because
interval?
there is no interval C plus delta, C minus delta, where everything is less than it.
I would highly disagree.
Why?
Well, let's see. F of 2 is certainly less than f, oh, sorry, yeah, f of 2, apologies. F of 2. It's certainly less than f of x for any x within 2 plus epsilon and 2 minus epsilon. Right, you go to the right, you go to the left. That value is smaller than the other value.
Isn't I thought the theorems for local minimum and local maximum are only. They
Well-
guarantee it when the function is continuous.
That's correct.
So for a function like this, there is no guarantee that it's a minimum, right?
Right,
But it is a minimum because we can see it.
I think so.
Okay.
Now, the thing is, although this is interesting, I don't think it's something we really worry too much about. Right, like, I don't think your teacher's gonna ask you if this is a local minimum on an exam, unless your teacher Molossi. No one has Molossi this quarter, so fine. But. Yeah, I think the answer to this first question is yes, I think every local minimum is a local minimum.
So one quick question on top of that,
Mhm.
just relate that. So we had a homework question. Trying to look it up right now. So we have a function,
Okay,
f prime of x is given by square root of x, x minus 6.
sure,
I mean, we are not given f of x, so we only have that one. What we are given is that the domain of f of x includes the endpoints for f prime of x.
And sorry, so what?
It says that, I'm using the exact wording, assume that the domain of f of x includes its endpoints. It doesn't say it's referring to what, but I assume f prime of x.
Okay.
So domain of f of x includes the endpoints of f prime of x.
Mhm.
So I assume that means 0 and 6.
Well, I would say, I would make the assumption that the domain of x is this.
Not positive 6?
Why do we need n at 6?
Oh, right, that's just a 0. Yeah, my bad. So if that's correct, then we ask for critical points of f of x,
Mhm.
and 0 is not a critical point in the correct answer. It's only 6.
Really?
Yeah,
Why, because you can't do like the square root of 0?
You totally
I
can do the
mean-
square root of 0.
yeah, that's why it's weird, because it says domain of x, f of
And-
x
and let me
includes the
see.
endpoints.
Problem with this.
It was problem, I don't know the number, but it was the last homework, attempt.
Oh, it's 10. Come on.
2 points and logbooks. I think, I asked him about it. And if I understand the answer correctly, it's because there's no domain around 0. And if I answered his answer correctly, there was nothing to the left of 0. So it couldn't be a critical point.
Hmm,
But I'm not sure.
well, so let me ask you a different question then. If your function is f of x equal to the square root of x,
Um,
is 0 a critical point?
no. It's
Why not?
It's
because it doesn't exist before 0.
So I guess, I mean, I feel like we're at a place where some people might define it a different way. Because at least, and again, I guess I should start bringing it up to 5. Because the way I'm, right, I feel like we've defined critical points, but maybe I'm forgetting something about it, them being within the interval and not an endpoint. But yeah, I would certainly think. Root is 1 over 2 root x. Times 0 is undefined. 0 is in the domain. So I would think 0 is the point.
Even though the function is undefined for less than 0.
Even though the function isn't defined for less than 0.
So one question, and then we should move on from this.
Okay.
We're spending way too much
Yes,
time on it.
I agree.
So for the endpoints, should we assume that they're critical? Could they be?
You should
critical?
assume whatever your teacher wants you to assume.
Okay,
So that might be different for different people.
sure.
Endpoints are always kind of a dicey situation, but let's move on. So let's look at this handout. We can kind of go wherever we want in this handout. I was going to start with some limits, because limits are always, you can see, I feel like this does a decent job of kind of covering the gamut of stuff that we've talked about over the quarter. So let's look at this first problem. The limit as x approaches 3 of the square root of x plus 1 minus 2 over x squared minus 9. Clearly a 0 over 0 type of limit. Now the question here is, basically the question I would think of if you have limits on your final is, should I use L'Hopital's rule or not? Totally, it's applicable here, right? You can definitely use L'Hopital's rule because it's 0 over 0. Is it the right thing to do? It might be, it might not be. Let's check. So if I take the derivative of the top and the derivative of the bottom, you make sure you're not using the quotient rule, right? Just the derivative of the top, derivative of the bottom separately. Derivative of the bottom is 2x. Okay, great. So what I can see for sure here is that it's either going to work or it's not. That's a dumb thing to say. But meaning at this stage here, I can't use L'Hopital's rule again because my denominator isn't going to be 0. So I'm either going to stop here and try something else or stop here and get an answer. Because I'm not going to get 0 over 0 again.
If you get 0 over 6, it's 0.
Right.
Is that bad?
No, it's only if I need 0. So then the derivative of x of the square root of x plus 1 or x plus 1 to the 1/2 is 1/2 x plus 1 minus 1. And then we plug in 3. Because every time you use L'Hopital's rule, you should then try plugging in your value. If I plug in 3, I get 1/2 times 4 to the negative 1/2 over 6. Square root of 4 is 2. 4 to the negative 1/2 is 1/2. So you get 1/2 times 1/2 over 6, which is 1 over 24. which is certainly what you would get if you did it the other way. The other way being like multiplying by the conjugate of this and factoring the bottom. That's definitely the not as easy way in this case. There's questions, don't hesitate to ask them. All right, the next one. Ooh, interesting. The limit of x approaches 0 when x times 1 minus cosine x over sine u of x. Interesting. It's always good to at least think about plugging it in and seeing, make sure you do actually get 0 over 0. Right, because there might be a tricky one with that 0 over 2. But this is a 0 over 0. Sine cube. Here's what I would say about this. This looks, I could try using L'Hopital's rule. Let's see what happens. Sure. So L'Hopital's rule. Limit x goes to 0. Here the bottom is going to be, let's say I got some stuff cubed, so it's 3 times my stuff squared times the derivative of my stuff. So 3 times sine squared x times cosine x. On top, I have to use the product rule. It's going to be 1 times 1 minus cosine plus x times the derivative of 1 minus cosine is positive sine. Yeah. And now things are looking like crap. Because the top is still going to 0 and the bottom is still going to 0. So this is an example of a problem where, although you can use L'Hopital's rule and it will eventually work, it is god awful after the second step. Or after the first step. We shouldn't do it this way. The intention here is for you to recognize you can write things as like sine x over x. I should also remind everybody, because it's probably been a while, but I should remind you all that the limit x goes to 0 of 1 minus cosine of x over x is equal to 0. That is also a very well-known limit. Let me show you how, in case you've forgotten. The way you show that something's equal to 0 is you multiply by the conjugate. So I'm going to write this as the limit of x goes to 0 of 1 minus cosine x times 1 plus cosine x. 1 plus cosine x. No chalk, a little chalk, it's been so long. So then, what's 1 minus cosine is 1 plus cosine? Sorry, but let's take the intermediate step and take 1 minus cosine squared x all over x times 1 plus cosine x. And then that's equal to the limit of x goes to 0 of sine squared x over x times 1 plus cosine x. And then that's equal to, we break it up into convenient pieces. Sine x over x, the limit we know is 1, calm down. And sine x over 1 plus cosine. That's 1, and sine of 0 is 0, and cosine of 0 is 1, and 1 times 0 is 0. Okay, so then, all right, I'm going to try and make this into convenient pieces. So I'm going to definitely break up an x over sine of x, because that limit is also 1. And I have a 1 minus cosine x, and I have another sine of x and another sine of x. And then I also need a combined line. All right, have I changed anything yet? Well, not yet. Have I changed anything? No. Okay, so then I would like an x here. So then I'm going to put an x here to balance that. And I guess I would like, I'd like this to work. Like an x here, which means I gotta put an x here. I'm concerned. Yeah.
Wouldn't it be a lot easier if you have sine squared x into 1 minus cosine squared x and just 1 minus cosine 1 plus?
That might be the way to go. I think you're doing this, this might not work out.
Because you have 1 constant.
Right, because I have a 0
And then everything has to be
times infinity. What if I just did this instead? No, that's not right. Yeah, maybe you're right.
That the answer would make a lot more sense.
Let's see. So I will point out that that is a good technique as well, is if you see a 1 minus cosine or 1 plus cosine or 1 minus sine or 1 plus sine, multiplying by its conjugate is often a good thing to do. Do that, we get x times 1 minus cosine times 1 plus cosine is sine squared. Yeah, that's the stuff. Because then we cancel 2 of those and 2 of those. X over sine x goes to 1. And 1 over 1 plus 1. Cool. Good job. Yeah. So, but definitely, if you see that your first step using L'Hopital's rule is really, really terrible and it's just going to get worse, probably means, especially if the sine and cosine, it probably means they want you to do something more with using the fact that the limit is x is 0 sine x over x. I feel like I saw a hand somewhere. Yeah.
So really quick question, I think they are equivalent, but I just want to make sure. Instead of conjugate by the conjugate, after we already separated x over sine of x, could we just rewrite sine squared as 1 minus cosine?
That'd be, yeah, that's
I
fine.
would just like to go.
Yep. Yeah, that works well. The same one, really. All right. Okay. The Zoom folks are hanging in there. Maybe I shouldn't go that far away. I'll go back over here. Let's maybe have a slightly better chance of seeing what's going on the board over here. I wonder if I could. Huh. I just had an idea. One sec. Let me do something to make it a little bit easier. Maybe see what's going on. Maybe we'll see. Let me do that. Turn it on. This might suck slightly less. Oh, that's a little better. Let's see if we do that. Oh no, you don't do that. Not that. Seems all right. There. I think I might have made it slightly better for your Zoom folks here. 1 second. Let me do this. There. I think that's a little bit better. Hopefully you guys agree. And maybe are still there. It's also totally fine if you decide to check out. I might have checked out too if I were not able to see much. Okay, so anyway, they can see a lot better now. So it's good. Let's do this next one. Oh wait, am I upside down? Oh my gosh. All right. Can I not be upside down? Oh my god. Ah my god, it's terrible. Let me see. I was so happy. I'm pretty sure I can rotate this. Yeah, go away.
It's been upside down the whole time.
No, I wasn't using this before. Yeah. Can we do this? Oh wow, that's yeah. Okay, hopefully now you all can actually see. Yeah, that should be better. Cool. Okay, now it's not upside down. All right, let's do this next limit. The limit, the next approach is 0 of the inverse tangent of x minus x over the inverse sine of x. I feel like this. Oh, is that better rhythm? So this is definitely a question that's really about your ability to remember the derivatives of the inverse trig functions. Because it's for sure L'Hopital's rule question. We've definitely got 0 over 0 because the arc sine of 0 is 0 and the arc tangent of 0 is 0. We're going to use L'Hopital's rule. I don't know what else you would do here. I don't think there is anything else to do. So L'Hopital's rule, okay. I'm probably going to L'Hopital's rule twice. The derivative inverse tangent is 1 over 1 plus x squared. The derivative of x is 1. And the derivative inverse sine is 1 over the square root of 1 minus x squared. And the derivative of x is 1. And it's still 0 over 0. So, So if I had to do this, I really would probably try to avoid doing it as is.
Wait, why is it 0/0? Because if it's 1/1 plus zeros, oh,
Right? So, but we do check, but we plug in 0, and we get 1/1 minus 1, 1/1 minus 1, yeah, 0/0. So I would probably do a little bit of simplifying here. I would try, because I don't want to take the derivative, I mean, you could, I guess it's not that terrible. No, ooh, no, it is terrible. Because I think if we don't simplify here, we're still gonna get 0/0. Because if you take the derivative of this, 1 plus x squared to the -1, you get -1 plus x squared to the -2 times 2x. And the 2x that's on top is gonna go to 0. And same deal down here, you're gonna get a times 2x, but those will cancel out, I guess. I don't know. Yeah, let's do it that way, fine, it's terrible. Let's do some slight rewriting to make our lives a tiny bit easier. Let's write this as 1 plus x squared to the -1 over 1 minus x squared to the -1/2. Then if we use L'Hopital's rule again, we're gonna get the limit of x to the 0 of -1 times 1 plus x squared to the -2 times 2x over -1/2 times 1 minus x squared to the -3/2 times -2x. And then you can cancel the 2x's. And then if you plug in 0, you're left with -1 times 1 plus 0 to the -2 over -1/2 times 1 minus 0 to the -3/2. 1 to any power is 1, so you're just left with -1 over -1. Oh, I forgot the minus sign out here. Don't forget the minus sign up there. I've got -1 over +1/2, so I get -2. Interesting.
so that what you just did was just doing a L'Hopital's rule from that above,
Like, exactly, yeah.
okay.
Now, what I will say is, I would probably have actually taken the route of simplifying this and then done it, but this works just fine.
Is that intended there for you?
I don't know. Intention is nice, but in the end, it doesn't matter if you can get to the right answer.
Sure. Just thinking like. is there a way that we-
I don't think there's a trick. I think you could. Sure. So let me be a little bit more. So from here to here, I use L'Hopital's rule again. And I said the derivative of 1 plus x squared to the -1 is -1 times 1 plus x squared to the -2 times the derivative inside, which is 2x. And 1 minus x squared to the -1/2 is -1/2 1 minus x squared to the -3/2 times the derivative inside, which is -2x. The 2x and the -2x, I cancel the 2x's. The negative sign is still there though. So then I'm left with a plugging in 0, -1 times 1 plus 0 is just 1 to the -2. And on the bottom, negative, let me clarify this a little bit on the bottom here. -1/2 times 1 minus 0 to the -3/2, which is 1 to any power. And then we do have that -1 right there. And then simplifying, I really just got -1 on top. And then -1/2 times -1 is +1/2 on the bottom. -1/2, -1 divided by 1/2 is -2. That's how I look at it. Yeah, you probably could simplify this, but I don't think we need to do that. All right. Let's look at the next one. Oh, yeah, I like this next one. Forgot how much pot gets everywhere. So, let's see. Limits are good because you're probably keeping limits on your final. Limit as x approaches infinity of 3x minus the square root 9x squared minus 4x. Here's an example of an infinity minus infinity. What do we do?
Multiply by the conjugate.
Right. Not just the conjugate, times over the conjugate, of course. Can't multiply that as anything. Let me make sure that this can. Try and keep this in focus here.
Wait, this would be 3x minus that or 3x?
Oh, yeah, good call. Plus, yeah, conjugate. So then. On top, the whole point of multiplying the conjugate is so that we get 9x squared minus quantity 9 squared minus 4x. On the bottom, we've got 3x plus square root 9x squared minus 4x. And to simplify, we have the limit as x goes to infinity of positive 4x over 3x plus the square root of 9x squared minus 4. Now what? Why not use L'Hopital's rule?
Why do you use L'Hopital's
Fair question. That's an excellent fair question. Well, in fact, the reason why you shouldn't use L'Hopital's rule here is I don't think it actually. If you try to use L'Hopital's, so let me just point out, if you try to use L'Hopital's rule here, well, at least I think it doesn't work out. I'm not 100% sure. I know there's one like this that don't work out. We try using L'Hopital's rule, which we can, for infinity over infinity. Top's going to infinity, bottom's certainly going to infinity plus infinity. So we try using L'Hopital's rule. Let's see what happens. Limit x goes to infinity. Top's going to derivative is 4. The bottom of the derivative is 3 plus. Okay, here the derivative of some stuff for the 1/2 is 1/2 times my stuff. So the negative 1/2 times the derivative of that stuff, which is 18x minus 4. Which looks kind of not bad. What I would actually point out is that specifically this part here, that looks like 18x minus 4 over the square root of 9x squared minus 4x. You're kind of back in the same, it's not exactly the same, but you're in a very similar place that you were just before. And if you keep taking derivatives of things like this, you're going to keep getting things like this. It doesn't ever really work out. So even though you could try to use L'Hopital's rule here, sometimes L'Hopital's rule actually doesn't get you anywhere. You can just keep doing the same thing over and over and over again, never getting an actual answer.
If you look at easy way, like good date when that's gonna happen.
No. I know it often happens when you have a limit to infinity and you got like a square root on the bottom. Like that's a frequent time where L'Hopital's rule doesn't tend to. He's basically kind of flip flopping back. Yeah, an easier example to kind of see that if you were doing like a limit, like x goes to infinity, or something like 2x over the square root of x squared plus 1. I think that one keeps flip flopping back and forth. You use L'Hopital's rule here, the limit's going to be 2 over the derivative of that is 1/2 times x squared plus 1 to the minus 1/2 times 2x. And that ends up being the limit is x goes to infinity of 2 times the square root of x squared plus 1 over x. You essentially just flip the whole thing. So if you look at the rule again, it's going to flip back the other way. Yeah, interesting. Now it's kind of like, so here instead we would divide everything by x, or what I would probably personally do before I divided everything by x, I would factor out the x squared from back here. I'm gonna have 4x over 3x plus the square root of x squared times 9 minus 4 over x. And then limit x goes to infinity of 4x over 3x plus what's the square root of x squared? Right, absolute value of x, but in this case, if x is positive, it's just x. And then you can either divide everything by x or factor out an x if you like. We didn't really ever do it that way, but you could totally just factor out an x from the top and an x from the bottom and cancel those x's. It's really the same thing. And then you can let x go to infinity and you're left with 4 over 3 plus the square root of 9 minus 0, which is 4 over 6.
question about one of the previous examples.
Sure.
It was for the limit as x approaches 0, actually, we have it written down. For 1b,
Yeah,
is that always gonna result in some kind of, like, identity?
often, yeah, when you have like 1 minus cosine or 1 plus cosine or 1 minus sine or 1 plus 1 plus sine.
Is it the same with like tangent and secant?
It's a good question. Oh, that's a good kind of thing. I'm trying to remember, there's a good.
One, that's one.
No, there's another, there's something. No, that's not a good example. Yeah, so. For example. Someone could ask something, I'm gonna make it. I'm thinking something else, so it might not turn out great. But. Someone could ask something like, what's the limit as x approaches 0 of. Secant squared x minus 1 over 2x. X squared. Which certainly is 0 over 0. And one way, the harder way to do this would be to use L'Hopital's rule. So if I start using L'Hopital's rule. Secant squared again. Your secant squared is 2 times my stuff times the derivative of my stuff. X squared is 2x. And at this point, you could either try using L'Hopital's rule again, or you could recognize that you have a tangent x over x. The limit of tangent x over x is x goes to 0 is just 1. That's going to end up being 2 times 1 over 2, all times 1. Now, what we could have done in the beginning is say, oh, secant squared x minus 1 is just tangent squared. And then you can write that as tangent x over x and tangent x over x. And each of those limits is 1, so you get 1 times 1 is 1. That would also be a way of doing it.
What did you do? Oh,
I use a tree identity,
oh, I see.
and then we know that the limit x is 0, tangent x over x is 1.
Oh, okay, cool.
That works too. Yeah, let's do these last two limits. If you see other problems on this handout that you would like to, or like for me to tackle, we should definitely do these last two limits.
Is there a master sheet?
There's not.
Oh, it's saying.
I can write one if I find the time to do it. There actually, as I said, there might be an answer sheet somewhere in our files. I don't know where it is. I can look for it. I might have the time to write one. When are all your finals?
Monday.
Monday,
Thursday.
Thursday,
Yeah, innocent class.
Next Friday.
Friday.
Wednesday.
What is that?
So all over the place. Okay. Yeah. I'll be dropping. I guess I'll try to post my dropping hours on Canvas. Not try. I
Is
will.
Kim still gonna be tutoring next week?
Yeah,
Okay.
in dropping. So all the help from the ATC will be located in dropping, which is over in the library.
So like C class and.
Right, all in dropping. There's no, we won't be in C class, we won't be in any other place, we'll be just in dropping.
Okay.
Fair question.
That's from like 10 to 5, right?
Ish, I think that's from 9 to, I think maybe 9 to 4 or 5.
Okay.
Yeah, so. And I'll say, the drop-in hours are already posted on, for finals week, on the AATC website. The individual specialist hours are not posted, and I don't know if they will be, but I will certainly post mine on Canvas.
After this, can you do 3 and 11?
Sure. I'm gonna do this one and the next one, and then, yeah. So limit and x goes to infinity of x plus 4 over x to the 3x power. Okay. If you see a limit that has a power, you should probably assume, or at least make a relatively educated guess, there's probably some sort of indeterminate form. It's probably either a 1 to an infinity, or a 0 to a 0, or an infinity to a 0. And this happens to be a 1 to an infinity. This part here is going to 1, as x gets bigger and bigger and bigger, and this power here is definitely going to infinity.
I mean, the inside goes to infinity with infinity.
Which in this case is going to one.
Right.
Is that
How do we know that?
You you all, the limit as x goes to infinity of 2x squared plus 5x plus 3 over 7x squared plus 9x plus 1.
Oh,
You would tell me it's what?
Yeah.
Yeah, because the powers are the same. Oh, the powers are the same. Or you could also rewrite it like. That's also totally valid.
Good thing we're having this conversation.
Right. Which is how I actually would write it, because I know eventually I'm gonna have to take the derivative of this part inside, and I'd rather take the derivative of 4 over x versus x plus 4 over x plus 4. So. We're gonna rewrite this as. The limit is x goes to infinity of, all right, we know that when it's an indeterminate form and it's exponential, we have to do the whole e to the natural log thing. We're gonna write this as e to the natural log of 1 plus 4 over x. Not the natural log of e to the stuff. It's not gonna work out. The reason we do e to the natural log is so then we can bring this thing down, because the whole problem with this exponential thing is it's exponential. You don't want it to be exponential anymore, so back then. Then we have limit x goes to infinity of e to the. Now, instead of writing 3x times the natural log of 1 plus 4 over x, we know we want to get a fraction. So instead of doing this, I think it's perfectly reasonable to skip that step if you feel comfortable with that and go straight to e to the natural log of 1 plus 4 over x over, you have a choice here. It's not a big choice. You can either write it as 1 over 3x, or you can leave the 3 up here and write it as 1 over x. I never before really noticed you could do that, to be honest. I've always written it as 1 over 3x, but it's probably easier to just leave it up there.
Why would you want to do that instead of just having 3x?
Like instead of having this,
Oh, wait, never mind.
Right.
Yeah.
right? Because taking the derivative of this is a little more, like, it's just, it's more,
Yeah.
it's easier to leave that 3 up there. Okay, now we finally get to apply L'Hopital's rule. Because not that you need to check this, because you have one of these 3 indeterminate exponential forms. You know that when you do this e to the natural log, or we do know when you do this e to the natural log, then you will get either a 0 over 0 or infinity over 0. Specifically here is a 0 over 0. That's going to 0 for sure. 4 of x is going to 0, 1 plus 0 is 1, natural log 1 is also going to 0. Cool. So then take the derivative of the top. You get 3 times 1 over your stuff times the derivative of that stuff, and the derivative of 1 is 0, and the derivative of 4 over x is negative 4 over x. And the bottom derivative of 1 over x is negative 1 over x squared. And those cancel. Almost always happens that way. Then I would evaluate the limit at this point. So you're going to get e to the, let's see, 3 times 1 over 1 plus 4 over x goes to 0. And then I've also got this positive 4 out here. This is a positive 4 because that negative sign cancels with that negative sign there. So let's say we get e to the 12th power.
That's fast.
Yeah, very fast. But what that means is, right? Well, I don't know.
So that's the answer.
Yep.
To the 12.
Yep. You can also do it the other way, where you just take the natural log and then your answer would be 12, but then you have to say, oh, my answer is e to the whatever I had to do the 12. Yeah. I don't like doing it that way because it's easy to forget that, but either way is fine. I feel like this is a lot more to write. Whole e to the thing, but
Would it help at all if we distributed the 3x in? So we have x plus 4 to the power of 3x. Could we apply the root just to that? Because that was just infinity.
so one more time.
So let's say we distributed 3xn, so we have x plus 4 to the power of 3x divided by x to the power of 3x. Could we show that the top and the bottom approach infinity, and
They're
therefore,
definitely about the protein infinity, yeah.
so could we just apply orbital roots to that?
You could.
Would it give us the same answer?
Well, let me ask you, do you know what the derivative of x to 3x is?
Just put L and Y because.
That seems like
3x.
more work. That seems like way more work than what we did,
Okay.
right? But really, like,
Logical.
right, you could, yeah, sure, you could totally use L'Hopital's rule here, but to find the derivative of each of these things, you have to be like, okay, y equals x to the 3x, natural log of y equals natural log, right? It's,
Yeah, it takes that.
and then, right, it's not less, it's probably more. But you're not wrong, you could see it as an infinity over infinity that way if you wanted to.
So infinity to the power of infinity is not independent.
Correct, infinity to the infinity is infinity.
Okay.
So someone said, what's the limit? If x goes to infinity of x plus 2 to the 3x squared power, that's just infinity. Big number to a big number is a big number.
It's only one. to the infinity.
Right. Specifically only one. Anything else. Like for example, if someone said, what's the limit as x goes to infinity of 2x plus 3 over x to the x power.
How about one approaching from the right? That wouldn't happen, huh?
What do you mean one person on the
I
right?
was thinking about a number that's slightly greater than one to the infinity,
How much bigger than one?
that as a limit approaching one, but from the
That's
right.
one.
That's one.
Yeah.
Okay.
I mean, that's one to the infinity. It's in triple.
Okay.
Okay, so you said 3? Yeah. Look at 3. Ooh, yeah, good question. These are good one. I mean, they're all not bad. So let's see here. So find A and B so that this function, which is ax squared plus bx plus 6, when x is less than or equal to 2, and bx cubed plus x, when x is greater than 2, is differentiable everywhere. So before we can even talk about differentiability, to be differentiable, the function has to be right. So we need to build continuity first. Now, this is a place where I would choose to be more formal, but other people might choose to be less formal. If you're looking for continuity here, what we're really concerned with is the left and the right side meeting up at 2. One way I would show this is that the limit as x approaches 2 from the left, using this piece, has to equal the limit as x approaches 2 from the right. Give me this piece. But some people might skip that step and just say, yeah, plug in 2 to this, plug in 2 to this, set them equal to each other because that needs to happen. I would say that's dependent on how formal your teacher wants you to be. So that's the relationship we get. But let's see. Solving, I guess, I don't know. I would divide it by 2, I suppose. 2a plus b plus 3 equals 4b plus 1. 3b equals 2a plus 2. I don't know. Good enough for now. Yeah.
Just like for this and in general, if you were supposed to say like, show like evaluate, like you're finding like the left and right limits, like say it's 2, like you're, even though it's from the left and right, you're plugging in 2.
Right. You're not plugging in like a number that's slightly smaller or slightly bigger. You were actually plugging in 2.
Okay, because I've had a question where it's like, you're finding, I think it was like horizontal and like vertical asymptotes, then you're supposed to like evaluate them to like see if it's the same at that point. And then I was confused with you still plugging in this.
Yeah, with vertical asymptotes, it's a little bit wavier because when you're plugging in that number, you're getting division by 0. And so then we do think of a number slightly off just so that we can tell what sign we're actually dividing by, whether it's positive or negative. Yeah.
This might be a little bit of a stupid question, but I'm just trying to understand the limit again. We probably talked about this way over at the beginning of the quarter, but limit as x approaches 2 from the left, why do we plug in 2? It's not 2, it's
But
approaching 2.
we're asking, what the question is asking is what value is the function getting closer and closer to as x gets closer and closer to the left? So for example, right, if my function were, if I actually had, let's make, if I actually something like, 3x squared plus 5x plus 1 and 2x cubed plus 7, I'm pretty sure. This is some parabola, right? Right, maybe this looks like I draw some garbage here. And some other garbage here. Like that. So whatever this point is here, in fact, if I plug in 2 here, I get 3 times 4, which is 12, plus 10, which is 22, which is 23. And this point's probably bigger. Then what? I can't remember what numbers are the same. Not on purpose. Fine, change it. So I plug in 2 here. 2 10 to the 8 is 16 plus 9 is 25. All right. So the thing is that when I talk about taking the limit as x approaches 2 from the left, limit as x approaches 2 from the left of this function is equal to plugging in 2 to the left hand side and getting 23. What you're saying here is that as x gets closer and closer and closer to the 2 from the left, the function does get closer and closer and closer and closer to 23. Similarly, from the right, the limit as x approaches 2 from the right of f of x, you just get by plugging 2 into this function and getting 25. We're not saying the function is equal to 25 when x is equal to 2. We're just saying that this function gets super duper 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 close to 25 as x gets closer and closer and closer.
We can plug it in because we know that it approaches some value.
Right,
It's not
because
really-
if x is, if x is 2.00000001, my function is going to be 25 point lots of zeros 1. That's right, we can get close to 25. That's what's going on. All right, so now we've got one equation relating A and B. The differentiability is what's going to give us the other equation, because then we'll have 2 equations and 2 unknowns and we can solve the system. So let's see, how precise do I want to be here? So personally, this is where I would probably get less precise. I could see some people saying, well, if you're going to find f prime of 2, use like the limit definition. They do not think we should do, right? It'd be like, hey, it's the limit as a approaches 0 of f of 2 plus h minus f of 2 all over h. And then you'd have to go like both sides. I don't think that's what we want to do here. And so because plugging in 2 plus h for x is going to get gross. What I think we want to do is to be like, well, if I take the derivative, the upper part's going to be 2ax plus b. The lower part's going to be 3x squared b or 3bx squared plus 1. So then I want those to equal each other when x is 2, because I want the derivative from the left and the derivative from the right to be the same. So f prime of 2 should equal. I'm plugging in numbers. So as you get a plugging 2, 4a plus b equal to 12b. Right, because at 2, the slopes have to match up. So then I take this equation, plug it in over there. Right, yeah. You can go either way. I guess I might solve this for a. Say 2a equals 3b minus 2. And then plug in that there. So 2 times 2a. 2 times 2a, being lazy and not solving for a, solving for 2a, then 2 plus b equals 12b plus 1. And then we've got 6b minus 4 plus b, 12b plus 1. So 70. 5b equals -4 minus 1 is -5, so b equals -1. And then plugging that back in over here. 2a equals -3 minus 2. So a equals -5/2. So that's kind of the idea. It's basically saying the functions equal to each other at 2, and the derivatives equal to each other at 2, and then getting two equations and two unknowns. Yeah. Yes, definitely 11. That's where I was about to go next, because that's what he also asked for. So, yeah. And 12, probably, yeah. Maybe, we'll see. Yeah. Oh, yeah, 12. I was thinking 13. Let's go back over here so people on the Zoom can see it better. Okay, so. You remember. Let's see, 11. Find the dimensions of the largest cylinder that can fit inside a cone of radius 6 inches and height 12 inches. So my radius is 6 inches. My height is 12 inches. And so just as a point, I've actually thought about this problem from both ways. Like, you don't want to put your cone in sideways, or sorry, your cylinder in sideways. You want to put it in vertically. Like, you could try to put a cylinder in this way, like that, but that's not the right answer. It actually isn't the maximum volume you can get. I have done the work. It's a pain in the ass, but you can check. So there's my cylinder inside my cone. And let's see here. I'm going to say that the radius of the cylinder, I don't know it, it's r, little r, and the height is little h. And here's typically what you want to do when you've got these three-dimensional objects in the other thing. Well, first of all, what am I trying to maximize? Or am I trying? What am I trying to maximize? It says the largest cylinder. Maximize what the biggest what? Biggest volume, right? Typically, when you're talking about maximizing the thing, you're talking about making its kind of largest or highest dimension as big as possible. So if it was some sort of area, you try to be maximizing the area, right? If it's a three-dimensional shape, you try to maximize the volume. And the equation for the volume of a cylinder is pi r squared times h. As is typical with these optimization problems, the thing you're trying to maximize is usually going to be a function of more than one variable. It means you're going to have some sort of constraint. The constraint here being that the cylinder is stuck inside this cone. This picture, though, isn't super helpful. It would be more helpful is if I think about projecting it onto a two-dimensional plane. So instead of having a cone, I have a triangle whose height is 12 inches and whose radius is 6 inches. And inside of it, I've got my cylinder. That point right there is what the radius and the height is. So the point r comma h, if I'm trying to maximize the volume, that point should touch the cone. Right, I shouldn't have it low, right? If it's too low, I can make it higher. If it's too thin, I can make it wider. So that point should be on this line. And we can find the equation of that line. My y-intercept is 12, and my slope is definitely what? Let's see, over 6 and down 12. Rise over run is -12 over +6. The slope is -2. You could also like do right. 12 minus 0 over 0 minus 6. But I think we do that this here. So my equation of my line is y equal to -2x plus 12. Which means the relationship between my radius and my height is, well, that point is on that line. So height is equal to -2 times the radius plus 12.
You go over that one.
Yeah, for sure. So this is my, no, I didn't draw the whole cylinder. This is my 2D projection of my cylinder, right? And that cylinder, this like, right, the top of the cylinder is touching the cone, right? Like they're touching each other right here. And so this point, right, again, yeah, we're not really drawing it, but we're thinking of this as like that. Same deal there. Right? So that point is on the surface of that cone. Specifically, this line, we can find the equation of, because we know that this line intersects, if we center this, and we should center this on the XY coordinate system. So right, there's our origin right there. And I'm gonna up 12 to 0.012 over 60.60. I found the equation of that line, which was y equals negative 2x plus 12. And I said, this point over r, so an x coordinate of r, and up h, so a y coordinate of h, is on that line, meaning that point satisfies this equation. So I can plug in h for y and r for x.
So you're just like treating them as one.
Yeah.
Also a similar triangle.
We probably have some similar triangles here.
Okay.
But I don't think that's the way we want to go. Not that you couldn't, but I feel like it's not it.
So you could like have 6 minus r as that small side. And then you would have two
Sure.
triangles.
I think you're gonna, but I mean, you should end up with the same relationship though, right?
I hope so.
Right, so it's probably easier to try to find the equation of the line.
Okay.
So typically, if you can see that you've got a line through a point on the x-axis and a point on the y-axis, usually just finding the equation of that line is not terrible.
My professor would write it as like r comma and then the equation of the line, like as the point. Is
Sure.
that the same thing as you did?
Yep, exactly, yeah. That would totally be also true.
Okay.
Yeah. Yeah, I don't love that, but it's totally accurate. Okay, so then my volume equation becomes pi times r squared times negative 2r plus 12. Plugging in that the height is equal to negative 2r plus 12. And now your volume is expressed as a function of just the radius. And then we can try to maximize this by taking the derivative, setting it equal to 0, finding critical points, and then checking it to maximum. And then finding the other variable. So I certainly would I don't want to use a product rule. I'm going to distribute the r squared to those terms. Remember that volume as a function of r, I have to write that, is pi times r squared times negative 2r plus r squared times 12. And then we'll differentiate. Let's put pi out in front because let's see, derivative of that is negative 8r squared. The derivative of that is 24r. Set that equal to 0. I would factor out an 8r. 8 or 6. 6. Fine. Multiplying things correctly. Yeah. Sorry about that. So I've got 5 times negative 6r. I don't like the negative that I did, and I'm up here with an r. What are my critical values? 4, right. Obviously, 0 is not the right answer because a radius of 0 is not going to give you a whole lot of volume. So usually you probably get away without checking it to maximum. If you wanted to check it was the maximum, I would probably recommend the second derivative test. So just taking the second derivative. What we're gonna get, let's see. Pi times negative 12r plus 24. And if you plug in 4, you get pi times negative 48 plus 24 is negative. So our second derivative is negative. What does that mean? Concave down, which means we have a max or a min. Max. Now the thing is, if they're asking to find where you have a maximum, the thing, if you're finding the one thing that by 0 is not really a real answer here, it's going to be a maximum. You're asking to find maximum. So we have to have a maximum volume when the radius is 4 inches.
Do we need to use the fact that the value can't be greater than the value of the cone? Is that a constraint?
Kind of. I mean, we're more using the fact that this thing, I mean, yes, but also
It's like useful though, like is that the useful?
I'll mention another thing, but we should also, before we finish here, well, before we finish, we also need to find the other dimension. So we've got that the radius is equal to 4 inches, and then we're also gonna say that the height is equal to 2 times the radius. Plus 12, I think not right. Negative 2 times the radius plus 12 is gonna be also 4 inches. They're not always the same. What I will actually say, just so you're aware, is that when you inscribe a cylinder inside a cone, unless all things, like as long as it's a normal kind of situation, the radius will always be 2/3 of your cone's radius, and the height will always be 1/3 of your cone's height. So what we got here, the height is 4, which is 1/3 of 12, and the radius is 4, which is 2/3 of 6. Which kind of makes sense if you think about it, because when you type in the volume, the radius is twice as important as the height. Because you're squaring it and not the height. So it makes sense that we want the radius to be capturing more of its possible value than the height is capturing. The other way you could think about this, and I know we haven't talked about this much really, but what is this? You can also say, well, we know that the radius is bigger than or equal to 0 and less than or equal to what? What's the most the radius could be? 6. And if you actually plug in those values, well, the volume when the radius is 0 would be 0. And the volume when the radius is 6 would be also 0, because when the radius is 6, the thing is, doesn't have any height. You can also check, right? If you plug in 6 here, you're going to get 0. And if you factor out r squared or 2r squared, you're left with a negative r plus 6. Right, this is definitely pi times r squared times negative 2r plus 12. If you plug in 6, you get 0. Because the height would be 0. And then by the extreme value theorem, a function on a closed interval has to attain an absolute maximum and an absolute minimum. So the only other place where we could have it would be at the critical point, which is 4, and it's for sure true that the volume at 4 is positive.
You're just doing that instead of the second.
Right.
That's-
Right, exactly. So if we know that the volume if we know the function is defined on 0 to 6, you've got a critical value at 4. Well, that's your absolute minimum. That's also your absolute minimum. 4 has to be where your absolute maximum. I don't love that as much, but it's something to do. Right. What was the second part?
This is weird.
Oh, sure. It's a similar but more terrible calculation.
Why is it more terrible?
Because is it terrible? No, it's a cone inside a sphere that's the most terrible. A cylinder inside a sphere is not really any worse. But I can show you. If you're doing a cylinder inside a sphere of radius 6. So then the idea is you're still trying to maximize the volume. Welcome. And so the volume is still pi r squared h. But then your constraint, instead of the constraint from before having a line, your constraint now is you're going to be, I like to use this way personally. I'd say you've got this right triangle where you have 2r squared plus your height squared equals to 12 squared.
And then it should be on that.
Right.
Okay.
Now here's what's fun about this one though. And that one, we solved for h to put in the constraint because it was straightforward. What should we solve for here? To plug into this.
Great.
Well, right, because even though you could solve for h and plug it in, you're gonna get square. Whereas here, if you solve for radius, in fact, I might have, yeah, sure. You get 4r squared equal to 144 minus h squared. And then r squared is equal to 144 minus h squared. 9.4. And then stop there. Plug that in for that. So then you get volume equals pi times 1/4 times. And that's not too terrible.
Would it matter if it does for it? It would just be a more terrible expression, but.
So, one more time, doesn't matter what.
It'd be so solved for it.
No, it would still be the same result, but if you solve for h here, you're gonna get to the. H is gonna be the square root of 144 minus 4r squared. And applying that in for h, here, taking the derivative of that is just more effort.
Yeah.
Typically, you try to make the choice of solving for the thing that's easiest to solve for / plug in for.
For question 13.
Mm-hmm.
It says show that if limit as x approaches 0, f of x equals 0, and if it's a differential function, the limit as x approaches 0, f of x, the power of x equals 1.
Let's take a look at Tal's rule question.
Is it?
I think so.
Can't you just show that if you have a limit of a function, the power of a function is just something of the function to the power of the limit of a function?
Sure, but what's the function going to?
That, wait, couldn't we just move the limit to the power?
Well, the thing is, both the function and the limit are going to 0.
Okay.
What kind of limit is this?
0,
0 to 0, which is in determinate form.
To the power of, yeah, okay.
Bring that down,
Yeah,
and then
we should at the top is gonna equal 0 eventually, so we have e to the power of 0.
well. Here you got 0 times after log of 0. It's in determinate cells, so if you do this.
Right. After we do the loop total, we have to get 0 though, right?
I mean, I assume so.
Because the font, because the.
I'm right, okay, let's find out. Let's see what happens. We use L'Hopital's rule. What's the natural log of f of x?
1 over f of x times the prime of x.
Right.
We know prime of x there. We don't know prime of x.
That's okay. We know it exists because they said the function is different.
Sure.
What's the root of 1 over f of x, or f of x to the negative 1
Negative 1 over square root of x,
times,
the prime of x.
right? Flip multiply,
Negative. Yeah. Sure.
good question. All right, I should call it a day.
Yeah, thank you.
Good luck on your finals, everybody. I'll post my drop-in schedule shortly. And there is another review on Canvas posted that does have solutions. So even if I don't write solutions, this one, there still is another one that has some answers.
So Grand notes has one final.
So,
Practice,
what's that?
Grand notes. They have
Sure.
one practice.
I think it might be the same one.
Oh, you have